question 11, 2017, and the question is the lanthanide ion that exhibits color in aqueous solutions is option A lanthanum 3, option B europium 3, option C gadolinium 3, and option D lutetium 3. So you have to find out which ion, plus 3 ion in lanthanide, will exhibit color in aqueous solution. Now coming to the answer. For generating color, there is a requirement of electronic transition. For that electronic transition, we need unpaired electrons. In transition elements, we know that because of the crystal field, the d orbital will split it, and there is a chance of dd transition among them. After the dd transition, we have to look into the selection rules, whether they are spin allowed or forbidden. If they are spin allowed, then it will give color, obviously dark color. If they are not spin allowed, if they are spin forbidden, then you have to think about Laporte selection. If then they are allowed, they will give pale color. So we know that electronic transition between different orbitals will be necessary for generating color, and the electron which is unpaired will move very easily than the electrons which are already paired up. Now in the question, we have to find out the aqueous solution of color of aqueous solution of lanthanides. Now the valence electron will go into the F orbital of lanthanides. The general configuration of lanthanide is 4f1 to 40, 5d01, 6s2. This is the valence orbital. So similarly, like transition elements, we have to look into the F orbital here. Now the splitting of A orbital due to the crystal field is not similar like the D orbital splitting. It is quite different and difficult. So we will not go into that part. For simplicity, we will look into the unpaired electrons and empty orbitals. So in question, four different lanthanide ions are given. First, La3, and it is the configuration of La3 is F4F0. Then gadolinium 3. The configuration is 4F7. Then lutetium 3, configuration 4F14, and final europium, its configuration is 6. Now in lanthanum 3, no F electron, so no transition. It will give no color. In these two cases, first is half filled and next one is full filled orbitals. Here all the electrons are paired up. Here the electrons are not paired up, but it has attained one half-filled orbital configuration, thus extra stability. In ground state. High energy required for electronic transition. And now europium. The configuration of europium in simple order will be like this. So here there is a chance of transition. Why? Singly filled orbitals, and this is empty. So very easily from any one of these the transition is possible. FF transition. Thus, because of this FF transition from the singly occupied orbital to the empty F orbital, you can see here if one electron is transformed from any of these singly occupied orbital to the empty orbital, the configuration will remain same. There is no change in the configuration. It will be again 6 half-filled orbital and 1 empty orbital. Thus, no extra energy is required due to the change in configuration. Configuration will remain same. Thus, this is the spin also will remain same. The spin, that is delta S value, that is S value before transition and after transition will remain same. Thus, this is allowed transition. Okay. Spin allowed transition and no change in configuration also. Thus, europium-3 actually give color in aqueous solution, that is pale pink color in aqueous solution. So your answer is europium-3. This is your answer. For further reference, you can look into the lecture on periodic properties of lanthanides and actinides by Professor Debashish Ray, IIT Kharagpur. And this is the YouTube link of that lecture. Thank you very much.